Hello, my name is Will, and I wanted to talk about the Riemann hypothesis. I recently saw that it was a topic that was becoming popular on TikTok, and I thought, what better than to make a TikTok video about the Riemann hypothesis? I recorded one yesterday, but it was a bit longer than I wanted, and I feel like I got it 99% right, but I wanted to try again and see if I could get a better take and go a little faster. So I'm going to go through this rather quickly. The main idea of this video is just to give people an overview of my take on the hypothesis and this technique that I use to analyze it. And I can always make additional content and go from there. So this assumes a kind of college or master's level math background. And I have a degree in physics and a minor in math. I was always a little bit better at math. So I'm just going to jump into this and paraphrase. You're looking at a paper with my condensed explanation and some formulas all over it. There's a formal paper to go along with it. I can link it in the comments. But I just want to give the overall structure of how this thing works so that people can become familiar with it and explore it on their own. If you find this interesting, reach out to me if you want to talk or chat or leave a comment. Okay, so let's look at the Riemann hypothesis. And I'm going to go quick compared to what I did yesterday. So let's see how this goes. So for the Riemann hypothesis, you have a sum, the Riemann zeta sum, and you have to show that the real portion of the complex input can only be 1/2 to make that sum have roots. You only get zeros. Zeros or roots are the same thing in this case. And they say, when do you get these roots? And it only happens for a certain value of a part of the input. Okay, so the Riemann sum has its analytic continuation, but there's another sum which is also closely related to it, and that's called the alternating zeta sum. It's the same as the Riemann sum, it just has every other term as a negative. It's subtracted out rather than added in. And it's also known as the Dirichlet eta sum. So you have the eta sum and the zeta sum, or the eta is the same as the alternating zeta. And for the sake of the hypothesis, you can use either one. The eta, it's a known equivalence to the hypothesis. The eta shares roots with the Riemann, and they both have to have that special relationship where if the hypothesis is correct, the real portion of the input has to be 1/2, and why and how is what you're trying to figure out. So we're going to start with that relationship. So here in the beginning, you can see this is the eta sum right here. On the left, you can see the n to the -1 for the alternating part. And that's equal to this stuff, 1 minus 2 to the 1 minus s times the Riemann. And you get this just from reorganizing the Riemann for its even terms and bringing them over to one side. And you can show the relationship between the alternating part and the full sum. So we need to take this alternating part here for the sake of our proof. And we need to show when and where and how it gives these roots, which is just when is it equal to 0. Now I've replaced the complex number s, which you see here, with its full version, a real plus an imaginary, a plus bi. So there's our complex number, and we need to show why this a here is 1/2 and only 1/2 to give roots. So we're going to do that just starting from this sum right here and try to prove it and see how can we go about showing that this a has to be 1/2 to make this thing have roots. Okay, so we're going to apply Euler's formula. I joke. I grew up hearing Bueller, so I always going to say Euler. We're going to apply Euler's formula to the denominator. We're going to do complex division, and then we're going to simplify using trig rules. And that's all you're seeing in this section here. Here's the formula for the exponent to put it in trig form. The bottom part, the complex exponent, we're going to use that. Here's vector division, or the complex division, and here's that being carried out. And it leaves you with this. Here's our eta sum again, and we've made it equal to its real part. You can see the real part here with the cosine, minus its imaginary part in front of the imaginary number I here. And you'll notice I made a note here real quick. I changed the negative n-1 to a positive 1 when I worked this out on paper. My mind always just likes seeing it better that way, and it doesn't change anything because -1 to the n-1 is the same as to the n+1. That doesn't change the parity of the alternating signs. But you could do it with n-1 if you want, but that's all that's going on there. So I just did that out of convention. I preferred to see it this way. In any case, so you've got your eta sum, and you can show that you're just expanding it into its real and imaginary parts. And then where do we go from there? So I factor out a -1 to get rid of that extra 1, and we just get rid of that. And you can see that here where we've gotten rid of the extra 1 in the exponent. And the other thing that's going on here is I've split each of these into, we're going to examine the parts of these by their even and odd indices. So here we'll call this A, the real part, because that's the real part of the eta sum. And you can see here we replace the index with 2n minus 1 for the odd and 2n for the even. So we're just looking at the even and odd parts of the sum. And we're going to show how they relate and how that creates this system. So for the real part, we've got this, and this is its odd part and its even part. And for the imaginary part, B, which is this over here, we've got this, which is its odd part and its even part. And now for this thing to have roots, we need it to be equal to 0. And in the sense of a complex number, that's 0 plus 0i. We don't want any real part and we don't want any imaginary part. So we need this real part, A, to be 0, and we need the B, the imaginary part, to be 0. So we need both these expressions to equal 0 in order to have roots for the sum. Okay, so because we split this into the even and odd index, you can use that fact to condense down these negative 1s to the power. Negative 1 to an odd power will always be negative 1, and negative 1 to an even power will cancel and always just be 1. So using that, we can get rid of this negative 1 exponent stuff in the front and just rewrite our A and B as we have here. So accounting for the proper signs and everything, you get, and I'll let you guys check the arithmetic, but this has been, I've gone over this with people. The basic arithmetic should all check out at this point. In any case, do it for yourself and see, you'll get a better explanation of what's going on. But you pull out the negative 1, you consolidate it for its even and odd index, and you get this here, that the real part is equal to this even part minus its odd part, and this will be important in a little bit. And the imaginary part is its even part minus its odd part. And they're basically the same thing, except the real part is in cosines and the imaginary part is in sines. Okay, great. So we need both of these to be 0. And then all we have here on the right is we're labeling these 4 parts. Here you say the even part, the real even, the real odd, the imaginary even, and the imaginary odd. And that's just these 4 parts over here labeled. So we can do the symbolic manipulation more easily. Then we're going to just look at these even ones. We're just looking at the even part of the two sums that we're dealing with. And we can take this ln of 2n, the natural log of 2n, and use log rules to make it 2n plus ln of n. So we're just using basic log rules, and that will leave us with a cosine of something plus something, and down here a sine of something plus something. And we can use trig addition for the cosine and sine addition rules to expand that. And that's all we're doing here. So here we see we're looking at just the even part, A even, and just the imaginary even part, B even. And we've written them using, we've expanded the logs and then used the cosine and sine sum rules to write the sums like this. And you can see this minus and plus in the middle, meaning you could take each of these sums and split it into 2 more sums. And that's what we're going to do next. And all we're doing is expanding the sum using log and trig rules. You'll also see that there's some material out in the front here that is not dependent on the index. And so we can take that material and pull it out front as a constant. And that's typical when you work with sums. So we're going to do that next up top here. Okay, so we come up here. And here you see the even part again, the real even part and the imaginary even part. And we've pulled the constant material out front and we've split the sums in half because over that common denominator down here. You have this common denominator. And that's all that's going on here. And now if you look through these 2 expressions for the even sums, you'll notice that there's some repeating objects. The material out front here is the same as here. Out front here is the same as here. These 2 sums are the same, and these 2 sums are the same. So out of these 8 terms, there's actually only 4 building blocks, and we're just going to label them here. Same way we labeled these ones down here. We're going to label these 4 down here, or up here. So we're going to call the material out in the front, that's the constant material, that doesn't have any n in it, that deals with the constants, that's with the cosine. We're going to call that the cosine constant, Kc. Same for the sine. We're going to call that the sine constant, Ks. K is for the 2 constants. But then you have the sums. And the cosine sum is this one here, and the sine sum is this one here. So we've just labeled these for symbolic manipulation. And that's all we've done. We've just taken the eta sum where we started. We expanded it into its real and imaginary parts. And then we're just looking at the even values of the even parts now. And we've labeled 8 terms. Well, 10, I guess. If you count the real and imaginary A and B, you have all their even portions, which is 4 here, and these 4 up here, which is the constants and the cosine and sine sums. So between those 10 items, you now have enough to prove the Riemann hypothesis, and you can reorganize them and look at the system that you've created and start to do some logic on it. And the reason all this works, which is getting into the next part here, I'm going to jump ahead a little bit, but the reason behind this is because it turns out of these 10 objects that you just labeled, there's a recursive relationship between them. And they're actually items that are in terms of each other. And because they're in terms of each other, when you write down that relationship, it creates a system of equations that has to be followed for that system to be true. So that's what we're going to do next. In terms of the labels, now I'm just going to start using the labels a bit. We talk about here that the real sum is the difference of its even and odd sums, and the imaginary sum is the difference of its even and odd sums. What do I mean with that? Well, right here, we're saying the real sum A is the difference of its even and odd sum. Even minus odd. Even minus odd. So the imaginary sum is the difference of its even and odd sum, respectively. So we're going to write that down with our symbols. The real sum A is the difference of its even minus its odd sum. And the real sum, or the imaginary sum B, is the difference of its even and odd sum. And that has to equal 0. We said the real part has to equal 0, and the imaginary part has to equal 0. So that's all this first line is right here. You've got the real part is the difference of its parts, and it has to equal 0. And the imaginary part is the difference of its parts, and it has to equal 0. Okay, but if that has to equal 0, then now we know that the even part has to equal the odd part. You could bring one to the other side up here, and the even and odd parts have to cancel out in order for when the whole sum is going to be 0, we want those parts to cancel out. Okay, well, what does that tell us? Well, we can look at those even sums, and we have an equation for our even sums up here. We say that the real even sum is equal to this stuff. We just broke it down, expanded it to look at it. And we have the odd even sum is equal to this stuff, broken down. We're just going to write that down using these labels we created. So that's all this system is here. You see the even stuff is equal to its constant times its cosine sum minus the other constant times its sine sum. And that you see the same pattern here. This cross, this is the same as this. This is the same as this, crisscross. You can see that here. This is the same as this. This is the same as this. The minus and plus sign are the same as the minus and plus sign. So we've just taken our expression for our even sums and we've used our symbols to write it down here. Okay, so where can we go from there? Well, here's the one. I would say there's kind of like 2 tricks in this proof that makes it work, but here's one of them. This is one of the key logic things that you have to come to understand, and I would suggest you try to play with the sums and do it yourself to become more familiar with it. But it's this recursive relationship that makes the whole thing work. We're going to go back here for a minute, and when you look at this real sum and its imaginary sum, and we say it's this part minus this part, and this part minus this part, out of curiosity, what happens if we put a plus sign here instead? What happens if we add these 2 parts instead of subtracting one from the other? What happens? And you'll find, well, this was when we split the index into even and odd. When we add them, we're just combining the index again, so we can run it over the whole index. And what do we get? Up top, this 2n goes back to an n, and this 2n minus 1 goes back to an n, and we're left with the same thing. So we get a cosine up top, and same down here, we get this sine up top when we combine this. And we say, hold on a minute, we just had a cosine and sine wave. And here it is, the cosine and sine wave. And you say, hold on a minute, what's going on here? So let's make this clear. It turns out that the even and odd portions, these right here, are you could kind of think of them as the building blocks for the system. When you subtract the even and odd portions in the right matter, respectively here, you get the real and imaginary sums. However, when you add them, you end up getting the cosine and sine sum. But these cosine and sine sums were part of the even sum. So you can see that there's kind of a loop there, where part of what makes up this even sum, when you add it with its even and odd part, makes up the part that's inside of it here. And both of those, when you subtract them, make up our original real and imaginary parts. So these things are in terms of each other, and we need to find the way to write it down correctly and figure out what's going on with this system. So that's what we do next. So we've already got our expression of our even sums here, but we just determined that this cosine sum, the one up here that we called C, it's its even part plus its odd part. And likewise for the sine sum, it's its even part plus its odd part. So that's all we're writing down here. The same way we said that the real and imaginary are the one minus the other, and they both had to be 0. Here we're saying that the cosine sum is the addition of those parts, and that the sine sum is the addition of those parts. But what do they equal? What's this other part back here? Well, we just determined from the fact that when they subtract, they have to be 0. That means that the even and odd parts have to respectively be equal to each other. But if those parts are equal, if I have like the even part plus the odd part, and they're equal, then that's adding 2 copies of the same thing. I could replace the odd part with the even or the even with the odd, and I'd either get 2 even or 2 odd. So we've shown that the cosine and sine sums can be represented by either twice of the even or twice the odd sum. Okay, so where do we go from there? Well, we use that fact to substitute for these 2 even values up here. So as we can think of the even sum in terms, the even sum is 1/2 of the cosine sum, or 1/2 of the sine sum. You can think of it that way. So when you do, you can substitute that in here. And what that does is now we have, instead of having a system that has constants, the cosine and sine sums, and these even portions, now we just have a system that shows the recursive relationship. We just have the cosine sum. We can see that it's equal to this, and that it's equal to 2 times constant, but times part of itself minus another constant times the sine sum, the other thing that we're dealing with down here. And so each of these two parts of the system are related to each other, and you can see that each one has a kind of recursive part related to itself. Okay, great. Well, what can we do with this now? So the goal at this point is, so all we've done is we've taken the Dirichlet-Eta sum, we've broken it into its real and imaginary parts to look at to expanded it into its real and imaginary parts, and then we're looking at the even portions of their input. And from that, we've gotten this logic that the even portion has to be equal to the odd portion to create their real and imaginary parts. But that part of them is this sine and cosine sum, and that they have this relationship here that has to be followed for these systems to make sense. Okay, great. Well, where do we go from here? The goal would be to solve for C or S or these constants and try to get a discrete form or a closed form for these things rather than a recursive relationship. Well, let's see if we can do that. If you look at this system, it has 5 solution sets, which I have down here. So these are the 5 possibilities for this system to hold arithmetically. So you can see if this, so you can solve this. One of these 4 or 5 cases has to happen. However, we're going to rule 4 of them out by way of contradiction rather rapidly. 2 get ruled out immediately, and 2 will get ruled out with a little bit of logic. So if you look at the 5 possible solutions to what are the rules on C and KC and S and all that, you'll get these 5 cases down here. In these first 2 cases, you can see that the sine and the cosine sums are related by an imaginary constant or minus an imaginary constant. Well, except for the fact that our original input is complex, all the other numbers and sums that we're dealing with are actually just all real values. We have this out in front of this, a little imaginary I here, but the value in front is real. And all these other things that we're dealing with are only take all real numbers and real values as their input. A and B are real, they're not complex. So, little a and b. So, we're not looking for any solutions that require the sums or constants to be imaginary. And in this case, the first 2 solutions are when they're imaginary related to each other, and that even makes one of the constants have to be imaginary too. Well, they're not, they're all real. So these 2 are ruled out because they're completely out of the range. We're not looking for complex results. That leaves us 3 real answers, 3 real possible solution sets. However, these next 2, where the KC constant has to be 1/2 and the KS constant has to be 0, That fact right there creates a contradiction on the rules that we apply to little a and little b. So little a and little b are our real and our complex imaginary portion of the initial complex input when we started up here. But a is only in the critical strip. And for the Dirichlet-Etta sum, the critical strip is considered to be between 0 and 1, but not including 0 and 1. So a, that critical strip, has to be between 0 and 1, but not 0 and 1. B can be whatever it wants as a real number. Okay, so where's the contradiction? So we're going to look at that in the next column. And then this bottom part is the solution set we're going to use. This is the one that's valid completely within our domain. It's real answers, and it's within the domain of A. So let's explain why these two are ruled out, why they show that A is outside of its domain. Now, you can get the paper and look at the full explanation. I condensed it a little bit here, but I'll go through it verbally and logically. And you can do it on your own and double check. This isn't anything that a college graduate couldn't do. So the reason that A ends up being out of bounds in those two solutions is really due to these two constants right here, the sine and cosine constant. If you notice, they share the same argument in the trig functions, this b log 2 or b natural log of 2, b natural log of 2. Well, these two solution sets require that the ks constant is 0 and the kc constant is 1/2. So when you come here and look at that, to make this ks constant 0, this top part has to be 0, which means that whatever bln2 equals, it has to be a multiple of pi. So whenever that's a multiple of pi, this whole thing goes to 0. Okay, but that shares the same argument over here. So when this is a multiple of pi and this goes to 0, this top part goes to plus or minus 1. And that's what causes the contradiction. Because if this top part becomes plus or minus 1, then that means plus or minus 1 over 2a has to equal 1/2. Because that's the other requirement, that it equals 1/2, that first constant. And when that makes, when those two are equal to, when that constant is equal to 1/2, that makes in order for plus or minus 1 over 2a to be 1/2, the a has to be 1 or complex. And a is not complex, and 1 is outside of its domain, which is between 0 and 1, but not including 1. And that's what this whole paragraph is here. There's 2 or 3 ways you can show that, and I'm going to go through 1 or 2 of them real quickly. But what you're seeing in these next 2 paragraphs is basically what I described right there. If you take this equation right here, our system that we made, which is just the expression of the evens in terms of the cosine and sine sums, and those constants, you'll see that you can start here. You can solve for C or S in either one of these, substitute it in the other one to have one equation with 3 unknowns, and look at the behavior of what that says about the relations of those items. And when you do, you'll get this formula here, which I'm not going to go over fully, but you get this relationship here. When you plug that into the other equation, you get this relationship here. And you'll notice that this says it has to be this quadratic times C equals 0. Or if you would solve for the other variable, it ends up being a quadratic times S equals 0. And okay, well, we already know that C or S would have to be 0 in that case. That would leave you with this solution or this solution. C can't be 0 in this one. But we already kind of ruled this out logically with our argument about the cosines and sines. Now we're going to look at it another way and also rule this out again. The other option here would be for the stuff in the quadratic to make it 0, this in the parentheses here. So when you look for when that's 0, you get this over here, and you see another contradiction comes up within that quadratic itself. And again, why that ks term had to be 0. And the reason is ks takes a real value or 0, but it's just still a real value. However, there's this minus 4 in here because of how the quadratic is. And that would make this whole thing imaginary, which makes this constant imaginary, which again, it's not. And that's where you kind of get these imaginary answers over here. So that means this has to be 0. The only other option here to cancel that negative out onto there is to make this 0, which then makes this 1 plus 0 over 2, which is just a half. And so that's that relationship of why it has to be 0 and 1/2. But again, you're back to the same contradiction, because once it's 0 and 1/2 and the arguments are the same, it makes A equal to 1, and that's outside of its domain. And that's all you see in this last little bit here. 1/2 equals plus or minus 1, what I explained, over 2A, which means A equals 1, and that's outside of its domain. So that only leaves this possible case here for that system where we want to examine it in the critical strip. It says that the two sums have to be 0. The cosine constant is 1/2, and the sine constant is free to be whatever it wants. So, let's see. And I don't know how well it's picking it up. In the very background, there's a goat who lives outside, and sometimes it bangs on the door here. So if you start hearing that, that's a goat banging on the door. I can't do anything about that at the moment. But anyway, okay, so we're going to look at this last case here when these are the requirements on the system. And you can take this same system and rearrange it another way. And instead of having it like this, we're just doing a basic thing and bringing constants to one side and sums to the other. And when you rearrange it for the value in the equation, which ends up being 1/2, you take all the numerical values, you put it on one side, and you take all of the sums and constants and put them on the other side in each of these two in each of these two equations here. So just bring all the numerical material to one side and all the symbolic sums and constants to the other. You'll get this right here. You get the Kc minus the Ks times this equals 1/2, and the Kc plus the Ks times this equals 1/2. So the only way that this can happen is when this term here equals this term here. That is, when the ratio of those sums, the sine and cosine sum, are negative reciprocals of each other. Or you could think about that like via cross multiplication, as the squares have to be negative of each other. But that never happens, because those are both real numbers, and when you square them, whether they're positive or negative, one side's going to be negative and the other side's going to be positive. And so you don't get any solutions. The only solution, again, is when they're just both 0, and you plug 0 back in this form, and you get this solution case here, back to why C has to be 0 and S has to be 0. But what about this Kc can't be 1/2, but it can be anything else, and Ks is free to be what it wants? What's the relationship between them, and how do they drive the system to 0? So we're going to talk about that next. But in between here, I make this one statement here. I say A equals B equals the even real equals the odd real equals the even imaginary and equals the odd imaginary equals C equals S equals 0. What am I saying here? This is just a logical recap of what we've determined so far now because of our system. So what we're saying is A and B have to be 0. That was our initial condition. The real part and the imaginary part have to be 0. Great. We're saying that because the only valid solution to our system here has to have C be 0 and S be 0. That's why you have C and S are 0 here. But we determined that C and S are just twice the even and twice the odd. So those have to both be 0 now too. So we've shown that in this system, all these parts have to be 0, but the only parts that are free to kind of do what they want are these constants. There. When the system has these solution sets and when it holds, or when it creates a system that's either going to all go to 0 or not. That's the rules that the constants, or this is what the freedom that the constants have in that state. And so we're going to look at that a bit more. So we're going to take this same set that we've been working with, and instead of pulling all the numerical material to all one side and all the symbolic material to the other side, now we're going to pull all the sums to one side and all the constants and the numerical material to the other side. So you just put all the sums on one side and everything else on the other side. And when you do, you get this representation here. There's the goat again. She's still out there. She's pretty cool. So when you put the sums on one side and the constant and numerical material on the other, you get this. But these items have to be the same as each other because they represent the same numerical data and the same value. So when you equate these two, you can cross multiply, and you end up with this relationship that now is a relationship just between the constants in those building blocks, that system we were using, the cosine constant and the sine constant. And this is the relationship that the constants have to follow in this condition here to make this system hold. If the constants have that relationship, then this can hold, and you can have this case here with c equals 0 and s equals 0. Okay, great. So where can we go from there? So we have an equation here, one equation and two unknowns. Well, wouldn't it be nice if we could find a second equation with those two unknowns so that we can try to say something concrete about the values of those constants? That would be nice. So let's see if we can do that. And it turns out we can. And the way we're going to do that is with the odd sums that we haven't really used as much yet in one way. So we originally just looked at the even sums back here, and we broke them down with our log and our trig rules, and we just wrote them down nice and neat up here. But you can't do that with the odd sums. This 2n minus 1 in here on the odd sums makes it in the log, makes it very hard to work with, and it just doesn't simplify or work with real easily. But it turns out that we can use this relationship here to write the odd sums in terms of the cosine and even sums, or the sine and even sums, respectively. And then we can use that to make another system of equations. So that's what we're going to do. So here you could see the odd sum would be the cosine minus the even if you brought that over to this side. And this odd sum is the sine minus this even if you brought that over to that side. Well, we know that those odd sums have to be 0 because C and S have to be 0, which makes 2 times those 0. So because these odd sums have to be 0, we're going to use that fact to build our next system of equations. If two items are 0, then when you add them together, you still have to get 0. And when you subtract them from each other, you still have to get 0. So that's what we're going to do. We're going to take this odd real part and this odd imaginary part. And let's go up top here. And here you can see we're going to add the odd parts together, and that has to be 0. And we're going to subtract the odd parts from each other, and that has to be 0. So we've made the requirement that since we know that the odd ones have to be 0, we're saying that, okay, well then we should be able to add them together, and it should still be 0. And we should be able to subtract them from each other, and it should still be 0. But now we substitute in what our value for the real odd part is, C minus AE, and our value for the imaginary odd part, S minus BE, and we add them and we get this equation. And likewise over here, when we subtract them, it just flips the signs on these last two, and we get this equation. But then like we did before, we can substitute the even parts up here now using the other part of the relationship, the 2s part, which we did back here. And when you do, you get this new system of equations for the odd sums that are just in terms of those constants again. No, I got ahead of myself. Here. So this is the system you get for the even sums, just by their definition, what they are, and by substituting that even part with the cosine and sine. And this is the system you get from the odd sums, recognizing that their sum and difference has to be 0. Great. So now we're going to do the same thing we did as before with the other system and see what quadratic we get out of this system. So like before, there's 5 answers. 2 are ruled out immediately because they're complex. And these other 2 are ruled out for the same reason as the other ones. The A ends up being out of range, or out of domain, technically, I should say, like I said. But in this case, you'll notice before it was 0 and 1/2. In this case, it's 0 and 1. And before, that 0 and 1/2 meant that A had to be 1, which was just outside of the range on the critical strip, between 0 and 1, but not including it. In this case, A ends up being 0, the other side of the critical strip, but still just outside of it, not including that value. So in this case, A is 0, which is outside of its domain. So we don't want these two here. I didn't show all that, but that's the same steps we did over here. I show a little bit of it, but not as much. But again, you can look at that in the paper if you want. So here you see that if you rearrange for C or S in one of these and then plug it into the other, you'll get this relationship here. And you get this quadratic, and it has to equal 0. When you look at what happens with this quadratic when it equals 0, you'll see that you get that contradiction that A has to be 0, which we're not interested in. But this bottom case, again, is a valid solution. And it matches our others. Both the C and S sum have to be 0. The sine constant is still free to be whatever it wants. And the last one, it said the cosine constant couldn't be at half. Well, here we say it can't also be 1. Okay, great. So where do we go from here? Well, like before, you can bring all the sums over to one side and all the constants and numerical material to the other side in those two equations, and you get this right here. And when those values have to be the same. And when you cross multiply them, here's your quadratic. Well, awesome. Now we have two equations and two unknowns. We have one quadratic, which represents what has to happen. This rule has to be followed between the system constants for the even system to make sense. And this rule here on this quadratic has to be followed for the odd system to make sense. But we need both those systems to make sense simultaneously. So we need both of these rules to be followed, both quadratics. So we're going to attempt to solve them simultaneously. So now if you've worked with enough systems of equations like this, in two equations and two unknowns, you'll know that you only get unique answers if the two equations that you have are completely linearly independent from each other. If one is just a scaled version of the other, sometimes you'll just get back one of the equations or a relationship between your two variables, but you won't get distinct solutions. And that's what happens here. This quadratic is a little different, scaled, but very similar to this quadratic. And it turns out we get a relationship between these two constants, and we have to keep digging a little bit further, but it turns out it's not much more. And so we're going to look at that. So here's the two quadratics that we just had. And you'll notice that this middle term, this 4kc, is the same in each one. Well, we can get rid of that just by subtracting simultaneously, solving both these simultaneously, and subtracting one equation from the other. So if I just subtract this bottom equation from the top equation, we get rid of the 4kc, and when you rearrange it, you're left with this right here. You'll see that the cosine constant squared plus the sine constant squared has to equal 1/2 for both of these things to be true at the same time. And if you have the condition that the sum of the squares of the constant equals 1/2, then both of these quadratics will fall into place at the same time. And both of your systems will be true at the same time. Excellent. So where can we go from here? Now this is where the proof falls into place. So the sum of the squares of these constants has to be 1/2. Well, we have the squares, we have the names or the labels and what those objects are back in the very beginning. Here's the first constant and here's the second constant. We want to know what is the sum of the squares of those things. We could have just gone back to this point out of interest and said square this and add them together and see what we get. Well, let's do that. And that's the next part. So here, you'll see the sum of the squares of the constants. Here's our cosine part squared. That cosine constant turns out to be this. Here's our sine constant squared. Turns out to be this. And when we add them, we conveniently get our trig rule on the top with a cosine squared plus a sine squared. So the top goes to 1. And the common denominator on the bottom is the 2 to the 2a. Because it was 2 over a squared. So we're left that the sum of the squares of the constant is equal to 1 over 2 to the 2a. And it's not dependent on the little value of b, the little b, which is the imaginary portion of the complex input. That ends up canceling out, and b is free to be whatever it wants. But it turns out the sum of the squares of these values is directly dependent on the value of a that you pick. But wait a minute. We just said that for both of our systems to hold true and to have the logical system stay intact where all the sums are 0, the sum of the squares has to be 1/2. So this 1 over 2 to the 2a has to be 1/2, which is what you see here. And of course, there's a little invisible 2 to the 1 power here just to make 2. So when you equate these two, you get 2a equals 1. And there it is. A equals 1/2. And a is the real portion of the complex input that we started with. And it comes out as the only solution of the woodwork of all those relationships. But it shows there that A is the only possible solution that will allow the sum of the squares to be 1/2. And that's the only possible solution that lets both of these quadratics hold true, which lets our system be true. And there it is. So I'll do a quick recap, but I hope you guys enjoyed it. I'd love to hear, what you think, or if anybody wants to talk. I've talked to people about this before. If you want to talk about it or have questions, hit me up in the chat or something like that, or get a hold of me on X. And so there's the proof and my take on the Riemann hypothesis and why the real portion has to be 1/2. And to re-summarize the logic, you just start with the eta sum. You expand it into its real and imaginary parts, A and B. You split those into their even and odd portions of their sums, of their index. You're just looking at those values. You express the even and odd. You expand that with log and trig rules. You express the even sums. You make the recognition that part of the even sum is, or that the even and odd sums are related to both of these, and that part of the even sum is related, the sum of the even sums is related to part of itself here. You write down the recursive relationship, and that's it. And then you have that system. You look for the rules of that system. You recognize that there's only one solution set because the others are all out of domain. The only solution set requires the C and S to be 0, which requires the even and odd parts to be 0. If the odd parts are 0, then you can get a second system of equations. You can examine both of those systems to find a relationship that the cosine and sine constants have with each other in each case. But both of those have to happen at the same time. When you do, you see there's a relationship that has to be held on the sum of the squares of those constants. But that because of the nature of the sum of the squares, because what those values were where you started with, that doesn't depend on the imaginary part, only the real part. And that this is the form that it takes. And for that to be the value it needs of 1/2, it also means that the real part itself has to be 1/2. And so there it is. So I'll leave it at that. I know this still took longer than I wanted again. It's about as long as the one I did yesterday. So I just would be talking too fast to get through it faster. But I'll leave it there. I hope you enjoyed it. And thanks for listening. All right. See ya.